Okay.
All right. Okay. Hi, everyone. Thank you all for joining today. Welcome to this week's AMA. Most of you may know that just a few days ago, ZKM's research team released a new white paper with design details about ZK MIPS. So we're joined here with Lucas from the research team. He's one of the main authors of the white paper, and he'll be able to answer all your questions about it. So if you have any questions at all, please feel free to put them in the chat, or I think there's like a raise your hand feature in this as well. So you can do that, whatever you're most comfortable with. I'll give it to you, Lucas, to introduce yourself.
Okay. Hello, guys. My name is Lucas. I work for ZKM in the research team. I I have written most of this white paper, so I'm the person behind it. And if you need someone to blame, it's me. But also, I like to state that this white paper is a work in progress, and we really want your feedback and we want questions because this white paper will change a lot in the coming weeks. We will release the final version before FCC in July, I think late July. So there's a lot to change until there, and any feedback is really welcome. And any questions, so please, if you read and if you have any questions or feedback, send them in the appropriate channels, and I'll be pleased to uh, reply to you. Okay, so I will make a quick presentation about the white paper. I'll not go through the white paper because I think that's a lot to cover here, and I don't want to bore everyone with the content of the white paper because it's really detailed. But I explained what's new in this white paper and why we chose to write a new white paper for ZK MIPS. We had a white paper that we released about 1 year ago, I think. And since then, since we started implementing ZK MIPS, a lot has changed. We made a lot of choices that weren't described in the white paper. We didn't update it accordingly. And this new white paper tries to can you still see my screen?
Yes.
Okay. This new white paper tries to explain like our new architecture and the new techniques that we chose. Like we didn't include lookup in the first white paper. We didn't include key check. I think we also didn't talk about graph. All of these were all these decisions we made during implementation, and we are trying to explain what these techniques are, why they're important, and why we chose them. But still, this is a work in progress, so not all of this information is here, but it will be included in the coming weeks. Okay, I'll start with this diagram that shows basically the proofs that we use to create our final proof. In this layer here, like this proof, it will be a proof for the MIPS program that we are trying to prove, and we will divide this program into segments of a fixed size, and we will prove these segments individually in this layer, like these proofs here. They are proofs for segments. And once we have the segments proven, we join this pair of segments into blunt proofs that recursively will give us a final proof for the program. So yeah, this is the middle. This is the highest layer of like our off-chain proof. So we divide the program in segments, we prove each segment, and then once the segments are ready, we create the program proof. How we prove each segment? To prove the segments, we need lookups to prove, to show that the segment proof, it is correspondent to smaller proofs, which we call module proofs. The module proofs, they are a way to prove less operations per proof. We divide the operations of a segment into 4 groups: arithmetic, memory, logic, and control. This division is done accordingly to ZK MIPS opcodes. So we prove different opcodes in different modules. And this happens here in the lowest layer. And once these module proofs they are ready, we join them into one proof for the segment, and then we compose the proofs for the segments to create the proof for the program. Well, this is not new. Like we've talked about this several times before. There's a blog post explaining how we do this and why we use each of these different algorithms in each of these layers, and what's the purpose of these algorithms. And so this is the part of the white paper that is not new. It was in the previous white paper. Well, kind of. It was not like described this way, but we already had the segment idea then, and we also had the module idea, but we didn't use lookup. We didn't know we would use lookup at that time. And the new things about this white paper are basically the trace table, because the way we talked about the execution trace so far in blogs and in Twitter, we say that we have a trace table where we have one column for each register. In practice, this doesn't happen. We have like a virtual table in this format, but the actual trace that we prove is not like this. This table, like this table containing all registers, it is not in the main trace. It is in the memory. We change the memory every time we change a register, and the actual trace that we prove in the module proofs, and that we have to like look them up in the segment proof. It contains a lot of columns that are used for control, and we have like columns used to select the opcodes. We also have columns to store the values that we will operate in a given instruction. Like if we are trying to add the first and the second register and store the output to the third register, then we will have the values of these 3 registers in the main trace. But these registers, the other registers that we don't touch in that operation, they're not in the main trace. They are just stored in the memory. And in this white paper, we explain why we do this and what's the purpose of that, what we get from that, like what kind of performance advantages we can get from this approach, and how the actual execution trace is composed. This is explained in this white paper. I think this is the most important thing that we explain here, because like this is the point where the practice really gets confusing. It's really different from the theory, and it's very different from what we explained so far. It's an equivalent approach. Like it doesn't introduce any flaws in our system, because we can make sure that the register values that we are operating on the main trace, they are the same values from memory, but it's a different thing that we haven't explained so far, and it is explained in this white paper. And it's something that if you go to the code, try to understand the code, you will not understand this if you just read our blogs. You have to read the paper to understand why the trace is that way, where you can find the trace, and how it is operated. And yeah, I think that's the main thing that's in this version of the white paper. I'm working on an update to explain a new feature that we included, I think this week or last week, which is we changed the hash function used for memory proofs. We changed it from keycheck to Poseidon, and I'm working on a section explaining why we made this choice. We also implemented GKR, which is a modification to the Lookup protocol that give us some performance improvements, and we are producing a benchmark for this new version of the code with GKR, and we will include this new benchmark section in the coming weeks. And yeah, besides this, there's also like this table containing the actual trace. This is the columns of the trace. Here we can see that the trace has 57 columns. If it had only one column for each register, actually we would need 2 columns for each register, because these columns, they are 16 bits, and the MIPS registers, they are 32 bits. So we will need 2 columns for each register, and since there are 32 general purpose registers, we will need at least 6 to 7 columns for the registers. But this would make the polynomials that we need to prove very complicated. So we chose to reduce the number of columns, the number of register columns, and increase the number of control columns to make the polynomials simpler. And that's one of the reasons why we chose this different trace. And I'm also working on a description of this new trace that I think will be released next week or the other week. And yeah, I think those are the main differences. I don't expect everyone to understand this white paper like completely right now, but I would really appreciate if any questions arise, if you guys can share this with us, so we can know where we can work, where we should work to like improve this paper and make it more clear for the community. Yeah.
All right, thank you, Lucas. We have some questions from the audience.
Yeah, I see.
Mhm. What are the limitations of ZK MIPS in terms of performance and scalability?
The limitations in terms of performance and scalability. Well, I think there's like a threshold for the complexity of polynomials and the number of columns, and we try to like make a choice that will optimize both, but we cannot assure that this choice, the way that we design the execution trace, is optimal. This is something that we are trying to do, and of course, like the technology behind all of these, the Stark, the Plonk, the library that we use to implement Stark and Plonk, which is Plonky2. is something that has an impact in performance. But like I think maybe the discussion is not just performance. I think we should also think about verification, because some proof systems, we can produce the proof, but we cannot verify the proof yet. And our proof is already verifiable. It's very like stable. We use this library Block2, which is very famous, and everyone like knows it works. So yeah, we are trying to optimize Block2, but there's much than performance to this discussion. But of course, performance is something that we are worried about, and we are trying to optimize performance while still like making sure that the final proof is usable, that we can verify it correctly, both off-chain and on-chain. So yeah.
Great, thank you, Lucas. Oh, I see Ming joined as well. So if Ming, if you want to jump in to answer any of the questions with Lucas, feel free to do so as well. We have another question from the audience. This one's about use cases and applications. Which application would you like to integrate ZK MIPS into? How can this improve existing applications? So if there's any like applications or use cases off the top of your mind that you would like to elaborate on, Ming and Lucas.
Well, I think that's more for Ming to answer. I think he's more aware of applications than I am.
Yeah, hello. Yeah, hello everyone. Ming here. So yeah, I think the question regarding what's the first one? I remember scalability. What was the first one? Alice.
Yes, the first audience question is what are the limitations of ZK MIPS in terms of performance and scalability?
Oh, performance and scalability. I think performance is can be described in terms of uh, the efficiency or performance of the prover regarding the verifier. The verifier is probably not so restricted because the verifiable computing scheme is to shift the burden of computation to the prover, and so the verifier can be a weak just employs a very weak computing power. For example, you can run the verification computation on a low power device, for example, an IoT device or your cell phone. That was the some of the pitches of these projects. And also, of course, in the case of blockchain, you can verify using a smart contract, so it won't consume too much computing power and cost. The prover performance, for now, I think that we're very fast approaching. Actually, as of now, like this week, the second major release, it will be just any days. So we have achieved, for example, like on par with SOTA, like state of the art. The benchmarks will be released very soon, any days, as I just said. So it's good. It's like it still requires a lot of computing resource, but at least like a memory wise and computing wise, it's quite accessible. That you don't need a top of the line and difficult to access computer, for example, like a Threadripper, 64 core, 128 core, or like 128 gig or more to 256 gig kind of rig to like humongous machine to generate these proofs. So just a regular consumer grade powerful machine that you can do this. Of course, then there's GPU, but the idea is that you can do both. GPU obviously will make a lot faster, but CPU is also doable because the technology should be accessible to many developers. And of course, we also have what we call like a proof network that people can, these kind of services can be utilized to supplement their own computing setup or power. So the numbers, I'm sorry, that we'll release very soon. But it's, as I said, it's on par with the soda. Just to be at the level that on par with these what industry projects at this level of complexity, because in order to talk about performance of benchmarks, you need to compare apples to apples. Certain like quote unquote like toy zkVMs are really fast, like they'd be 1,000 times faster, but those are only like toy CPUs, virtual machines. And we are probably the industry's first zkVM based off a real CPU. So that's immensely powerful and useful. That's the reason we chose the hard way. I think that's to answer those questions. Regarding scalability, these computations can be vastly, parallelized. So there's the context of scalability in talking about zkVM. So you can kind of divide a computation into many chunks, segments, and I think Lucas can probably explain more in this regard. Yeah, but I understand the scalability in this regard. Yeah.
Yes, we can produce like proofs for each segment in parallel. Like we don't have to produce them in the same computer, so this enables the proof market that Ming mentioned. We can like divide we can run a program and divide it in segments and ask different people to prove different segments, and then we can join all these proofs. Of course, this can be done for huge programs, but that of course that makes it more scalable, because the proofs, they are completely independent from each other. And we just had to run like the continuation proof to join this segments proof later, which can also be done in parallel. So we can, I can show this in diagram. Like this can be done in different computers, and then also this can be done in different computers. So one person can divide this segment in modules, ask different people to prove these modules, which don't make sense because the modules, they are really small, but like this can be done because the modules, they are dependent. And then different people can have their segment proofs joined using this continuation proof here. And like each of these small continuation proofs can be generated in parallel. So this allows the proof network, where a lot of people are working, are like proving small proofs that in the end will generate one single proof. And we don't have to like ask a single computer to produce this proof. That would take a lot of time. We can ask a lot of people to produce these proofs in parallel, and it will take way less time to produce the here, like the time that we need to produce the whole proof depends on the height of this tree, of this continuation tree, and not on the size, on the number of leaves in this tree. So yeah, this basically give us a logarithm performance in logarithm time using the proof network. That's one way to scale these proofs.
Thank you, Lucas, and thank you, Ming, as well. Ming, I'm wondering if you can answer one of the audience questions about applications and use cases. So the audience question is, which application would you like to integrate zkMIPS into? How can this improve any of our current existing applications?
Yes, sure. So the advent of zkVM or zero knowledge proofs in the blockchain crypto space is immense. There's a lot of use cases that's zero knowledge proof made available to us that unimaginable before. So let me kind of start from the beginning. So when you create a blockchain, right? What's the purpose? The purpose is to prove, the whole blockchain is to prove something, for the purpose of decentralization. Since the computation is decentralized, needs to reach a consensus. So in order to reach a consensus, you're actually building up a proof. So a ledger, the blockchain is a kind of proof. So there are a couple proofs that's involved in this in the blockchain space. So you need obviously from one block to the other block, there's states. So there's the state proof, right? So that's when you heard terms like Merkle tree, these, and also for Ethereum, for blockchain that has that have enabled smart contract capability. There's also the states are also managed with like Merkle tree, like called Merkle root, which actually is also used in like layer 2, because in that case the computation was carried out off chain. So you also need proof that these computations are carried out faithfully. This is where zero knowledge proof is very useful. Of course, zero knowledge proof virtual machine, so called zkVM or zkVM, which is the one flavor. There are many flavors of these things. So our new thing. So previously there are simpler zero knowledge proofs that can prove all kinds of properties that's useful to the blockchain and crypto application. But with zkVM or zkVM, you can prove a more general kind of computation, smart contract, and the flavor that we are doing implementing called zkVM is or can be considered more universal than zkEVM, because basically you can prove any computation use any computer language because they all compile down to MIPS introduction, like a CPU. So a CPU can run any computer language programs, including EVM. So for example, we can prove a full node. We can, not just a smart contract. We can prove like a full node of Ethereum, for example, Geth or mini Geth, which is a full node written in the Go language. Of course, there are other languages implementing full node, for example, Rust. And yeah, we can prove that too. We can even prove like non-blockchain programs. So you can pick any program written in the last 4 decades, long before Bitcoin, before the first blockchain smart contract. Those programs not related to anything that we do on the blockchain today, but they can be proved, and you can actually post that on blockchain as a way for people to prove facts to be able to put more information and application onto the blockchain. So the application is immense. Also, from a design point of view, there are very powerful mechanisms can be implemented with the help of this tool, the zkVM, because the zkVM proves a computation trace. It proves not just a simple message, as many more primitive zero knowledge proof protocols like before. With this, any state carrying computation, message, and information can be proved. And with that, you can actually build things not available to the decentralized applications before. For example, ZKM has built something called entangle rollup, right? So with rollup, you have ZK rollup, which is using the zero knowledge proof EVM or VM to prove the off-chain computation that to be verified on-chain. So this is a way to kind of scale a blockchain, for example, Ethereum. But with the power of zkVM, we can actually prove all kinds of computation, not just for a Ethereum EVM virtual machine. We can prove any other VM. So we can support more than just one blockchain. We can support interoperability among many blockchains, and also the interaction and the apps that's built on top of all kinds of blockchains. So this is a really powerful tool or infrastructure that our zkVM can enable. Of course, the limit is only the people's imagination. I'm sure there are other kinds of the apps that's not possible before can be enabled by this technology. Yeah, I think this is what I see the application of this technology.
Yeah, thank you, Ming. And I think a really important part to emphasize is that we can even improve non-blockchain programs and for applications beyond just simple messages. Basically, any program, which is pretty powerful. And I think this can be a good leadway into a popular question that we see quite a bit, which is why we're using MIPS. I'm wondering if Ming or Lucas, you can explain how ZK MIPS compares to other projects who are implementing what we're trying to implement with verifiable computation, like ZK EVMs versus ZK VMs, which you briefly touched on, Ming, but also projects using other instruction sets like with RISC-V. So basically, why is ZKM using MIPS?
Yeah, so let me start a little bit from the computer architecture side of this question, and Lucas can continue into cryptography side of it, or engineering part of it, because that's also a big chunk. The white paper actually, this new version of our paper actually touches some of that. So let me start with the computer architecture side. Why we chose MIPS. I already said earlier that the reason why we implement this is pretty hard, and there exists other sort of architectures, what we call like RSA, which stands for Instruction Set Architecture, called RSA, which is basically the instruction set for a specific CPU, could be real or virtual, right? And you can actually implement any ISA for any arbitrary, imaginary language, or it's kind of like a language. So it can be really simple. And for example, I think StarkNet has IRC called Cairo, which is really simple. Like I don't know about their newest version, but the simplest is like contains only like 7 opcodes. So naturally, this is very very easy to implement as a ZK VM, and it's really fast. I mean, like I once heard engineer from them claim that it's 933 times faster than Risreal in certain function, like some demo function, for example, maybe SHA-256 or that I forgot, but it's very fast. So why we implement these, right? Not just us, there are also other flavors of zkVM that adopts a more real like CPU, for example, RISC-V, right? The reason is the user space. So people have designed computer languages that claim to be really good. For example, Lisp, right? There exists a machine called Lisp machine before, but eventually, from the perspective of the user base, most of the programs are written in languages, for example, C, C++. In the blockchain space, Golang, Rust. Rust is really popular lately because it's very efficient at writing low-level code, and it's the code is actually more efficient than Golang as well. So these are very popular programs. Of course, also a lot of smart contracts are written, for example, on Ethereum are written in implemented in Solidity. So you can get away from this. So that's the reason to be relevant in the real world. You need to implement a zkVM that supports these. So MIPS is probably the first, ZK MIPS, which is the flavor of our zkVM, is probably the first zkVM that based off a very stable real CPU. There's of course, everyone heard of us would ask, why MIPS? Why not RISC-V? I think the debate between MIPS or RISC-V is a little bit like it's misleading, because here we're not designing the CPU, right? We're just proving a certain computation using CPU. So in this case, RISC-V's purpose is to be a competitor to ARM, right? ARM. ARM is a popular RISC based CPU architecture on for implementing like cell phone, right? So ARM has 232 opcodes. It's pretty complicated. RISC-V is actually trying to catching up. So different vendors, different manufacturers, because it's open source, it's open standard, so they can add their own flavors of instructions to make certain computations much faster. And so you'll have probably hundreds of these different custom RISC-V CPUs. The core RISC-V instruction set is only 47 opcodes. But if you just implement 47 opcode CPU, then it won't run anything, won't be very practical. And if you implement the zkVM based off that, you can use that to actually simulate the proof for any real program, because no program will be just implementing 47 opcodes. So in that regard, the RISC-V is just as any other those optimized, sort of like quote unquote optimized zkVM that doesn't have a counterpart in the real world. So why just doing something like Herald, right? Like optimized for ZK, because you're not building a cell phone here, right? You're generating a proof for a computation to carry it out in the blockchain world. So a better approach than that, I think, is actually this project called Valida. It's designed a CPU, like ZK optimized RSA or CPU, like virtual CPU. That's more complicated than Chiral, but it's vastly simpler than MIPS or RISC-V. And so that is probably the way then it's actually better than RISC-V, I think, because the current RISC-V doesn't have anything to do with the real RISC-V CPU, because it's doesn't really matching any of the vast array of RISC-V CPUs out there in the real world, right? And also, you're not doing that proof for cell phone, right? You're doing that for the blockchain, the apps. So in that regard, I think our MIPS flavor, zkVM called ZK MIPS, is the one that represents the real CPU, and it's very stable. Like in the paper has mentioned, MIPS 3000 actually is not changing for decades. So you can, as I said earlier, you can pick up any program, compiled binary from 30 years ago, and you can get it approved. And that computation can be proved and verified. So so this is the rationale behind why we implement this and why it's important. All right, so that's the computer architecture side of the argument. So Lucas, you can probably talking about the challenges and the why side of this from a cryptography and engineering point of view.
You mean like the challenge of modeling the MIPS opcodes?
Yeah. Why we do this? And it's everyone knows it's hard. But why we do this, and what's the method and that we adopted to make this work, to make it performance wise, that's usable. For example, continuation, and all kinds of considerations that we must solve.
Yeah, well, in that regard, basically, we chose MIPS because MIPS is stable, so it's easier to create polynomials that will model those opcodes, because those opcodes, they don't change a lot. So we have to model them once, and we can be quite sure that they will not change, because they haven't in like 30 years. For ZK EVMs, on the other hand, like EVM is changing all the time. So every time there is a change to the EVM instruction set, a new ZK proof has to be produced, or like we have to compile the EVM bytecode to intermediary language and prove this language. But like we don't think that's a good idea, because it would require a new level of a new level to the compilation process. So it can increase like the probability of bugs being introduced in the final ZK proof with time. And basically we can take advantage of the stability of MIPS to produce the polynomials only once. And once the polynomials, they are produced, like mathematically, we can be sure that the proofs will be correct. That we can like create proofs to show that two segments are equivalent to each other. We can create proofs that will I don't know, for instance, what graph does in this final level. You can create a proof that will compile a block proof to a on-chain friendly proof. And by using MIPS, we can be sure that the the complexity, the logic of the proof will be encoded as polynomials right away, and once it is in the polynomial form, like it's much easier for us to ensure the correctness of the program logic. So we remove like the dependency of higher level tools to make sure that the MIPS logic will be a polynomial logic as soon as possible, and from this we can just use like the protocols in the papers to make sure that everything is correct.
Yeah, thank you, Lucas and Ming. I also want to mention to everyone in the audience that Lucas answered pretty comprehensively why I think Barney had a question of why the program trace in the first layer doesn't need to be explicitly logged while the segment trace does. So if you're interested in that, check out his answer in the chat. I'm also wondering, maybe this is a question for Lucas. I'm wondering about the intention behind using the lookup protocol, and it would be also great if you could speak about a comparison between the lookup protocol that we use and maybe some other lookup approaches, like for example, like lasso and jolt.
Sure, of course. Well, lasso and jolt is very cool. They use a very different approach, and there's a lot we can learn from them. But personally, I think it's kind of risky to encode everything inside. Actually, it's not risky to encode everything as lookups. The problem is that the way lasso and jolt does it, they like the logic that we have to encode in these tables, it has to be very friendly to the polynomial encoding. That's not always the case for every instruction set, and to write the polynomials in that way, in a way that it's very easy to encode in the polynomial form, it's not something that it's easy to do, and they don't do it for an opcode with a complexity like MIPS, like they do it for a very basic opcode. So that's doable for them, for the instruction set that they chose, but it's I think it's not that it's not doable, but it would take a lot of time to produce proofs like this for the MIPS instruction set. It's already like complicated enough to model ISA like MIPS as polynomials. As polynomials that are compatible with lasso and jolt, that it will be like a whole completely different case. It will be way more complicated. And we use Lookup because Lookup was the best protocol. I think it's still the best protocol that we have for this purpose. And we use Lookup with GKR now. I think GKR is already live. This is something that we borrowed from Lasso and Jolt. They do use Lookup to some extent in part of their proofs, and they also use GKR. So also, I think they introduced the GKR. Like I think they were the first one that implemented. I think maybe there might even be the same guys who designed GKR. So yeah, as far as I know, I think Lookup is the best protocol, like by far, and Lookup with GKR increases performance a lot. And yeah, that's something that we do. That's something that Lasso does. That's something that a lot of proof systems that I've seen in events that I've done they do. Like this is becoming the default approach in the area. Yeah.
Yeah, thank you, Lucas. I'm also wondering if you can speak about like the intention behind using Stark in the lookup phase in terms of generating the lookup polynomials and proofs, and Plonk in the continuation phase. So maybe you could speak about like the intention or like why that choice was made.
Well, the criteria for this choice is basically how easy it is to create a circuit for the logic that we are trying to prove. And in the continuation phase, we basically have to create a proof for the Fried protocol. And the Fried protocol, it is highly recursive. So the instructions, they are repeated a lot. So it's easy, relatively easy to create a circuit for them. And the Plonk protocol, it does have a arithmetization form that requires a circuit in the first place as an input, whereas Stark do not require a circuit form. We can like create kind of a CPU like proof with Stark. Yeah, and like the difference is that the proof for a secret like logic is smaller because we can kind of run instructions in parallel. But it does have like this issue of needing to state your input as a circuit, and that's not very easy to do for CPU-like logic, as the case of MIPS, because of course MIPS runs in the CPU, so it does have like a CPU-like, a CPU-friendly way to describe it. And it doesn't have like a circuit-like, a circuit-friendly description. But we do have it in the case of Fry, so that's why we chose to use Plonk with Fry to increase performance a little, because we can run some instructions in parallel. That's not doable for the base proof, so that's what we chose to go with Stark for the zkVM proof.
Yeah, it's very interesting to hear about all the rationale and intention behind these design decisions, especially with all of the engineering challenges, all the trade-offs that come with it. So I guess a lot of thought needs to be put into finding that balance. So thank you, Lucas, for that answer. As a last question, unless if anyone else has any more questions in the chat, one audience question that we have, maybe this is more suited for Ming, is how can developers get involved with building using ZK MIPS? So maybe some next steps for the audience.
Yeah, I think the developers, you can definitely check out our GitHub, or the all of our social media outlets from zkM.io. There you'll find our papers, white papers, documentation, and also the links to our GitHub. So you can check them out. You can follow the instructions and try to generate proof of yourself. And also thinking with this zkVM that we developed, what new protocols, like more protocols you can design, what kind of like new the apps that you can develop. We have some our own apps that sort of as a demonstration. One is called the hybrid rollup. which we simply bypass the EVM altogether. We developed validity proof component relying on our zkVM. So sort of, as I said earlier, it's like proving a full node. So you can bypass all that compatibility issues of EVM, like type 1, type 2. For us, it's more low level, so there's no compatibility for EVM because we bypass the EVM altogether. And the verification is on layer 1. So yeah, that's the native EVM. And also, we also developed entangle rollup, which demonstrates the power because you can completely prove a whole state transition computation. With that, you can sort of frozen and transfer consensus on top of between all blockchains. So that's why we call this a bridgeless bridge, right? So there's just only rollup powered by zkVM, our zkVM, and because it's not limited to the EVM, right? You can support all kinds of blockchain. So the power of the EVM can be used in these demonstration, and obviously, I think it's limited by your imagination, and you can probably develop something even cooler. For example, we haven't even explored the space of like decentralized gaming, right? So previously, the gaming on blockchain is mostly just another shell of token games. But now, like imagine you can build decentralized worlds. You can use zkVM to kind of build the world logic between different decentralized user base, right? Maybe they can see different worlds in a different way, or you can implement game logic in a very decentralized way as well. So yeah, the excitement and possibility are unbounded. So just to give some example, of course, also you can probably implement a much more sophisticated, for example, DeFi applications, right? So I used to work with people who want to build a really sophisticated DeFi dApps. These people, they're from Wall Street, and they look at the status of Ethereum, and they say, "Oh, we can't really build this with EVM." But now, since all the computations with EVM are off chain, and with the with zkVM, that you can have a more complicated computation, and a lot, of course, the scale of the computation can also be vastly expanded, almost limitless. So this is the power of the rollup that's enabled by our zkVM. So I could probably talk about now for hours about this, but just check out our GitHub and try to start by generating proof yourself, and then thinking about what you can build on top of this fantastic technology.
Yeah, thank you, Ming. And maybe we can have a follow-up AMA to go into even more details. But yes, I posted the link to the GitHub, everyone, in the chat. So if you're interested in trying to generate proof for yourself, feel free to follow the proof generation and verification guide in our documentation. If you need any help, feel free to also ask any questions you have in the Discord, tag any one of us, and we'll give you some pointers as well. Okay, so we're at the end of the hour. Thank you, everyone, for joining today. And thank you also, Ming and Lucas, for answering all of our questions. Ben will be hosting a follow-up quiz where you can earn points. This will be right after this AMA, so be sure to check all the details in the quiz channel. And if you have any other questions that you think of after this AMA, there will be a Q&A document that we'll be sharing. Ming and Lucas we'll be answering those questions in text, and then we'll be sharing that document to all of you guys. So for any other questions that you have, please just send them to us, write them in the Discord. But other than that, thank you all for joining, and we'll see you next time.
Okay,
Thank
bye,
you.
guys.
All right, thank you, everyone.